Okay, so let me share my screen. Okay, so today I want to visit again the idea of first order linear differential equations. I'll give you a small taste of why one would even consider revisiting first order linear differential equations. These are, after all, the first things you kind of see in any course dealing with differential equations. So what's there to think about? Well, we learned that if you just consider real variables and real solutions, then the answer is not much. There isn't really much to think about in that case. However, you end up with things like, a solution of a differential equation will have two branches, and these two branches are disconnected branches, and you just have to learn to live with that. On the other hand, if you are not so narrow-minded and you allow yourself to consider complex value solutions, then, well, you get to do a whole bunch of other things. And these are far more rich solutions. And in fact, we saw last time around that we could take a very simple differential equation, which has a very simple linear solution, and show that depending on the coefficient in the differential equation, and in particular a parameter in the differential equation, you could get a completely different classes of solutions. Okay, so it turns out that if you allow yourself to consider A, complex valued solutions, with B, complex coefficients, there's a lot more to be said about differential equations, even first order differential equations, even first order linear differential equations. So our goal here will be to move on to second order linear differential equations, ordinary differential equations, I must add. We're not talking about partial differential equations here. So our goal will be to think about second order linear differential equations that one would typically encounter in mathematical physics. Things like Schrodinger's equation and things like that. But before we get there, let's see what we can say and what we can learn from just studying first order linear differential equations. So I want to consider today first order linear differential equations with complex coefficients. And what we're going to learn is that the structure of the coefficient function in these first order linear differential equations hold a lot of the properties of the solutions. And without even solving the differential equation, although in this case, because it's a first order linear differential equation, we'll be able to solve it, at least formally, in terms of an integrating factor. But the same story will hold for higher order differential equations. So it's good that we learn it in the case where we actually know what the solution is. And then, depending on how much time we have, I will introduce the idea of monodromy, which is tied to the idea that you pick up a phase change as you go around a point on the complex plane. Okay, these ideas of monodromy and monodromy matrices are quite prevalent in many fields in mathematical physics, from cosmology through to quantum physics. So I'll give you an introduction to what I mean when I say that in this case. Any questions? Okay, so let's see what we're talking about. So I want to consider the following differential equation. In fact, I'm going to use an acronym, and I'm going to use it a lot because it'll save me a lot of writing. So I want to consider the first order linear differential equation. That looks like dw by dz equal to, plus some coefficient function p of z times w equals 0. And the main thing I want to note here is that this function p of z will have isolated singular points. Okay, So it only has isolated singular points. So what I mean by isolated singular points is that it'll have some singularity. I haven't decided what that singularity is yet, but if it has these singularities, then I can always draw some neighborhood around that singularity such that I don't encounter another singularity. So that's what I mean by an isolated singular point. So what can I do with functions like this? Well, the first thing I could consider doing is making an expansion in a power series. Now, if I make an expansion in power series where all the factors of z are positive power, then we call this the Taylor expansion or Laurent expansion, depending on the choice I choose to make for about which point I expand. More generally, you would have learned that I can also include negative powers. And if I include negative powers like 1 over z, 1 over z squared, etc., then I get a more general series called the Laurent series. So let's expand this thing in a Laurent series. And I want to expand it about some point z0 in an annular region. So z0 satisfies that there's some value r1, which is less than mod z minus z0, the distance from z0, which is less than r2. So this is an annulus. It has an outer radius of r2 and an inner radius of r1, and our values of z lie in that annulus. Okay. So just for concreteness sake, the region in the complex plane will look like this. And we're considering all values of z that lie inside this region here. Okay. So this is some point z0, r1, and r2 on the complex plane. Okay. So what do I mean? What do I get when I make this expansion? When I make the expansion, I'll find that in this region, I can write P of z as sum from n equals minus infinity to infinity of some set of coefficients, let's call them an, z minus z0 to the nth power. Okay. So let's go to the next page. I need 1 second. So I'm just going to pause the recording for a second. Okay, sorry about that. I'm back, but we have a visitor who will be doing his homework next to me as well. Okay, can everybody still see my screen, my whiteboard screen?
Okay. Yeah, we can.
Good. Cool. So, all right, we're interested in what the solution of the differential equation is. Now, this is a first order linear differential equation, and the way you would have learned to solve this is by a number of methods. One of them would be it's a separable differential equation. I can take all the w's on one side, all the z's on one side, and then divide through by dividing through by w, and then I can integrate. Or I can write down an integrating factor and multiply it through and then integrate. Either way, the solution of the differential equation, of the first order differential equation, is given by, so the first order linear differential equation is solved by w of z equal to some constant times e to the minus the integral of p of z dz. Okay? And you can check that this solves the differential equation for any constant c. Now, it's the 19th of August. Right. We have an expansion for this p of z. So let's take that expansion, put it into the differential equation. Now, because I want to make a point here, and the point that I want to make is how the singularities, the role that the singularities play in this story. Because I want to make that specific point, I'm going to separate out this Laurent series. Remember, the Laurent series goes from n equals minus infinity through to n equals plus infinity with one special point, and that's when n equals 0. Okay, so that's a linear term. So I'm going to separate out all of the, it turns out that there's another special point, and this is when n equals -1, and n equals -1 is going to tell me about poles. So I want to separate out the Laurent series into its specific components, and we're going to deal with each of those components separately. So separating out the components, then I can write this as c times the exponential of minus a minus 1 integral of dz over z minus z naught. That's the -1 contribution, minus the sum, that's an ugly summation sign, minus the sum from n equals 0 through to infinity of an times the integral of z minus z naught to the n dz. These are all the positive powers as well as 0, minus the sum from n equals 2 to infinity of a minus n integral of z minus z naught to the minus n with respect to z. Very good. So there's 3 parts. One involves an integral that goes like 1 over z minus z naught. The other one involves an integral that goes like z minus z naught to the n, positive n. And the other one that involves z minus z naught to the minus n. Again, n is a positive number. I'm summing from 2 all the way through to infinity. So let's see. The first term is straightforward enough. That's just c times the integral, c times the exponential of minus a minus 1 log of z minus z naught, because the integral of 1 over z minus z naught is just log of z minus z naught. The next term is straightforward enough. It's the sum from n equals 0 through to infinity of the integral of z minus z0 to the n dz. So that's just an over n plus 1.
Yes, I'm confused on what happened on the second line.
What happened on the second line?
Yeah, because you said you were separating. What were you separating there? I'm not sure I understand what you were separating.
Okay, so I have a sum from minus infinity to plus infinity. Okay. N goes from minus infinity to plus infinity.
Yes.
I've separated that into a sum from n equals 0 to plus infinity.
Yes.
N equals minus 1. And n equals minus 2 all the way through to minus infinity. But then by changing the sign of n in that last piece, I can send n from 2 to infinity and just say a minus n. Can you see what I've done?
Oh, so you changed the. Oh, no, not quite. So you changed the sign of the integral and made it negative instead of positive. Because no,
Say it again.
I'm not quite sure I get what you just.
Okay, so let's go over it again. Remember, we have an expansion of p of z, and the terms go. I'm just going to write it down. Okay, so the terms go. Let's use a different color. From n equals minus infinity through to plus infinity of some function of n. Do you agree?
Yes.
Okay. What I'm saying is that I'm going to take this thing, break it up into the sum from n equals minus infinity through to minus 2, counting from minus infinity all the way up to minus 2.
Okay.
You agree?
Yes.
Same f of n. You with me?
Yeah, yes, I'm with you.
Good. Plus one particular term when n equals minus 1. So I go from minus infinity to minus 2, then
Yes.
minus 1, then the sum from n equals 0 through to infinity of this f of n. Are you with me?
Yes, now I'm with you. And then.
Good. So then in this first term, it doesn't matter whether I sum from minus infinity to minus 2 or from minus 2 to minus infinity. You agree?
Yes.
Okay. So I'll just change this from minus 2 to minus infinity. It means the same thing. I just write down all these terms, and then I add the terms. Whether I add them going that way or add them going that way, who cares? I'll get the same answer. You agree?
Yes.
Right. So now what I'm going to do is I'm going to say, now I'm going to let n be minus n. So this becomes a minus n there. And the limits of my sum will change from minus t to minus infinity to 2 to infinity. Do you agree?
Okay, now I see it.
You good?
Yeah, I'm good now. Thanks.
Great. Okay, so let's continue then. So the second term I integrated, and I got z minus z0 to the n plus 1. And of course, I'll have an n plus 1 in the denominator. And then the third term, I do something similar. And I'll get the sum from n equals 1 to infinity of a minus n minus 1 over n z minus z naught to the minus n. Okay, so what I've done here, you'll notice that as we just spent some time talking about now, with the sum going from 2 to infinity, and now I've suddenly gone to 1 to infinity, is I've just done the integration and I've shifted it by 1. So when I shift the terms by 1, I have to shift the limits of my sum by 1 in the same way that you do this with integrals. But the key point out of this is that this looks like some constant times z minus z naught to the alpha times g of z, where this guy g of z now is an analytic function. So that's the form of this solution, right? So as long as my function p of z has this structure, so just isolated singularities, I can write the solution of this differential equation as some constant, integration constant, times z minus z naught to some alpha, times an analytic function. So this guy is analytic, and analytic meaning analytic on C, which means I don't have any singularities there. Everybody with me? Okay, so let's look at the structure of the solution. Okay, depending on the nature of the singularity in P of Z, I'm going to have different forms of the solution. Depending on the nature of the singularity, in P of Z, we'll have the following. So let's split this up into cases. So the first case is, in fact, I want to phrase this differently. So depending on the nature of the singularity in P of Z, our solution, W of Z, has differing properties. In particular, if P of Z has so 1, a removable singularity. So who can remember what a removable singularity is? Anyone? Mika? No? No one? Take a guess. What is a removable singularity?
Then it's a point that we can, where when we integrate, move around or like try to avoid or take it out of the integral.
Okay, so let me be more specific. What is a removable singularity in terms of the Laurent expansion? How's that?
Isn't it a singularity of the order -1?
What do you mean by the order -1?
Where in our expansion we're using the subscript n, so
yes.
n equal to -1.
So n equal to -1.
When there's a singularity corresponding to that in the expansion, that's my guess.
Okay, William.
Is it not where there's a point on the function such that it's like undefined, but we can sort of redefine it so that we can fill in the missing point? Something
That
like
is what it is in words.
I just remember
Warren?
something from complex analysis about poles and residue. I'm not sure if it's the same thing, but I think it had to do with removable singularities.
Well, I missed the first part. You remembered something from complex analysis?
Yeah, where you had like these removable singularities, and then there was a way to make it regular about the point by using the poles and the residue. But I don't remember the process. But I know
Okay, so
those
not
words.
quite, but we're kind of getting there. Okay, so it certainly has to do with so I think the closest so far has been William, and Justin and Warren are telling me more or less the same things, but we'll get to that. That's a separate type of singularity. A removable singularity is one where all the coefficients of the negative powers in the Laurent expansion are zero. So in particular, what this means is that A minus n equals 0 for all n greater than or equal to 1. So A minus 1, A minus 2, A minus 3, all the way through to A minus infinity, all of those coefficients vanish. In other words, my Laurent expansion collapses to a Taylor expansion, right? And in words, that statement is you can redefine your function to remove that singularity. Is everybody with me? Anybody with me?
I think so.
Somewhat.
Cabello, what is that?
Yeah, I'm good.
Okay. Good. Okay. So what does this mean? Well, when I have a removable singularity, then my function w of z, which is the solution of my differential equation, is analytic everywhere. And in particular, it can be written as some multiple of this analytic piece g of z. Okay. And we say that this first order linear differential equation has a removable singularity at the point z naught. So if p of z has a removable singularity, then w of z is equal to this constant times g of z and is analytic everywhere and we say that the first order linear dE has a removable singularity at z naught. Okay, so that's the first one. Next, we come to the case that that Justin and Warren identified, which is what happens if P of Z has a pole. So when P of Z has a pole, then there are two types of poles we can encounter. One is a simple pole, and the other one is a pole of higher order. So let's start with the simple pole. So if P of Z has a simple pole, and what this means in terms of the coefficients in the Laurent expansion is that all of the A minus n's vanish for n greater than or equal to 2 in this case, and that A minus 1 is not 0. So A minus 1 specifically, and only A minus 1 is non-zero, everything else is everything with a minus n for n greater than or equal to 2, all are equal to 0. Okay, so we only retain the term with n equals -1. Well, in this case, the term that survives in my Laurent expansion after I've done the integration is the term that had the logarithm. Okay, so if we go back to the top here and look at what I get, this is the term that survives here, this log term here. What do you know about logarithms on the complex plane? Anybody? What do you know about logarithms on the complex plane? Take a guess.
Wouldn't it only be
What kind of singularity?
Would it only be in a specific part of the plane because the log couldn't have any negative inputs?
Well, what kind of singularity specifically? So P of Z has a simple pole. W of Z has what?
Wouldn't it just have a singularity at the origin?
Well, I haven't said anything about the origin here. I'm making expansions about the point Z0.
Oh,
So-
when Z is equal to Z0?
At Z equals Z0, I have a singularity, but my question is, what kind of singularity? Anyone?
Wild guess, removable singularity.
We have a very wild guess. We covered removable singularities already. Did you name me the kinds of singularities that you're familiar with, and specifically the ones that are associated with logarithms? Anytime you find a logarithm or a square root or a fractional power of z in a complex valued function, you always find this kind of singularity. What kind of singularity is it?
Is it an essential singularity? Is that such a thing?
There is an essential singularity. This is not it. You see, I give everybody a hard time.
So you're relying on everyone's memory.
Yeah, I am. Such as mathematics, unfortunately for you.
I'm just gonna Google it.
Branch point.
Ah.
Yeah, of course, yes.
Ah, branch point.
There we go. So if P has a simple pole, then W has a branch point at Z0. And if P and if the solution has a branch point at Z0, then we say that the first order linear DE has a regular singular point at Z0. Okay, so can you see how we're getting to the point where I give you some differential equation, you look at the differential equation, you look at its coefficient, and just by judging the coefficient, you're able to tell things about the solution. Okay, admittedly, we've solved it in this case, but in the more complicated second order case, the same story holds. And there, it's not so clear that I can just look at the differential equation and just get a solution by inspection. So we have one more case to consider,
Wait,
and that's what happened. Cabello?
Sorry for interrupting. Could you just underneath just give us an example of an equation that does have a regular singular point, and then just write an arrow that its solution would look like this as a branch point? Just an example.
We're going to cover an example coming up, and you've got a couple of examples coming up in the problem set. Okay. So I just want to go through the last point, which is that if P of Z has a pole of higher order, let's call that order M. So a higher order pole. A higher order pole, let's say of order some M greater than 1. And then in this case, so just call it, you can have a break. Then in this case, W of Z has an essential singularity at Z naught, and the differential equation itself has an irregular singular point at Z naught. Okay, very good. So now we've covered 3 cases. Either my coefficient function P of Z has a removable singularity, a simple pole, or a higher order pole at Z equals Z naught. And remember, we're thinking about this annular region here whenever we're talking about this function. Okay, the values of Z all lie inside this, the values of Z all lie inside the annulus, which has an outer radius of R2 and an inner smaller radius of R1. And so, and Z naught lies inside this region. And we're only interested in, sorry, not Z naught, Z lies inside this region. Okay. Okay. In which case, our differential equation has either a removable singularity at Z naught, a regular singular point at Z naught, or an irregular singular point at Z naught. Okay, so we've essentially classified all of these first order linear differential equations on the complex plane by looking at the structure of the singularities of the coefficient function P of Z. Now, in order to make this particular classification, we actually had to solve the first order linear differential equation. This was a pretty easy task because it's a first order equation, but higher order equations, as I said, are generally much harder to solve. So the question then is, can we say anything about the solutions of the first order differential equation, first order linear differential equation, without actually solving it? So that's what I want to do now. So the question I want to start off asking is, can we say anything, or let's phrase it this way, what can we say about the first order linear differential equation without solving it? Okay. And I want to do this through an example. So let's set out an example. And I want you to forget the fact that we solved the differential equation as this constant times the exponential of the integral. I mean, that was pretty formal in any event, and I had to actually tell you what the P of Z was if I actually wanted you to solve the differential equation. Okay, but now let's just forget we can write this formal solution, right? The first order linear differential equation has a unique solution up to a multiplicative constant. If you're deeply into your complex analysis, you can prove this, but it's not necessary for our purposes. The point I want to make here is that the solution is unique. So a first order linear DE has a unique solution up to a multiplicative constant. And that's the constant of integration. So suppose I have such a solution, and I'm going to call it W of Z. That means that any other solution, let's say V of Z, is some constant times W of Z. If W of Z is a solution, then any other solution V of Z can be written as some constant C times this W of Z. So that's what I mean by unique up to a multiplicative constant. Okay. So now suppose that, and we're considering the same differential equation, right? dW by dz plus P of Z times W equal to 0. So now suppose that this function P of Z has a singularity at Z equals Z naught. So we've got a singularity at Z naught. And I'm going to choose to write Z minus Z naught in polar form. So modulus argument form, I'll write it as R e to the I theta. Okay. So suppose we start at some point Z that's not equal to Z naught. And then we make a circle around Z naught. If we do that, then theta changes as we traverse Z naught. Theta will change from theta to theta plus 2 pi. Okay. And we'll end up with a function that in general will differ from the original function by this phase. So the new function, call it, let's say W tilde, is not the same as the original function. Okay, so let's see what I mean. So if we now we want to take how to phrase this. So now suppose we start at some Z that's not the same as Z naught, and circle Z naught. What are the consequences of this? Well, if we circle Z naught, then for one, the phase or the argument of z, changes from theta to theta plus 2 pi. If we go around in a circle, and w of z will change to some new function, w tilde of z, that's not in general equal to w of z. In particular, w tilde of z will be w of z naught plus r e to the I theta plus 2 pi. So remember that I'm writing z minus z naught as r e to the I theta. I'm encircling the point. So z minus z naught is r e to the I theta. So z is z naught plus r e to the I theta from here. Okay. And then what I'm doing is I'm encircling z naught. So theta changes to theta plus 2 pi. Hence, I get this factor here. And then I add to that. W is a function of z. Hence, W is a function of z naught plus r e to the I theta. And when I make this change, the second factor picks up this phase change. Okay. But we know already that any solution of the differential equation is up to a constant multiple, just W of z by uniqueness. Okay. It's just equal to W of z by uniqueness. And so that means that I can write this as some C times W of z. So again, I start at the point z, that's not equal to that's not equal to z naught. I traverse z naught in a circle. That changes W of z to some W tilde of z, and that W tilde of z must be, by uniqueness, equal to some constant times W of z. Okay, because in traversing the point, I haven't changed anything about the fact that we're talking about a solution of the differential equation. So W tilde is still a solution of the differential equation. So let's make a note of that. So this is still a solution of the ODE. And so it's bound by uniqueness. So now let's do the following. So now I'm going to define the number alpha through the following. I'm going to say that this constant C is actually equal to e to the 2 pi I alpha. Why I choose to write it like this, it will become clear just now. Okay, but I have a constant, right? That is the constant of proportionality in this relationship between W tilde and W, right? And I didn't tell you anything about this constant. In particular, it can be a complex constant. And so if it's a complex constant, let's write it as e to the 2 pi I alpha. Now, one thing here is that I didn't tell you that it had to be a unimodular constant. So the coefficient of this is 1 here. Okay. But you can show that even if it's not, I can always absorb that factor into the rest of the function, and in which case I might as well just consider something that looks like e to the I something. Okay, in this case, that something is 2 pi alpha. And I'm going to define the function G of Z through G of Z equal to Z minus Z naught to the minus alpha times W of Z. All right, the 3 lines there mean definition. So it's not equal to, I define it to be this. Okay, so again, I've defined a complex numbers alpha such that e to the 2 pi I alpha is the constant. And I've defined a new function G of Z, which is equal to Z minus Z naught to the minus alpha times W of Z, this unique solution of my differential equation. My claim here is that as I traverse Z naught by 2 pi, as I go in one circle around Z naught, the function G of Z is single valued. So the claim is that G of Z is single valued as we traverse the circuit. Why is this? This is true because as I make the traverse, G, which is a function of Z, and therefore a function of Z naught plus R e to the I theta, goes to G of Z naught plus e to the I theta plus 2 pi, which is R e to the I theta plus 2 pi, all raised to the minus alpha, because the thing inside the brackets there, this guy here, is nothing but Z minus Z naught. And that's how Z minus Z naught changes by the definition of G, times W of Z naught plus R e to the I theta plus 2 pi. That's just W of Z, or W, or how W of Z changes. So now let's break this up a little bit. In particular, I can write this as R e to the I theta to the minus alpha times e to the minus 2 pi I alpha times e to the 2 pi I alpha times W of Z naught plus R e to the I theta. Okay. The factors of e to the 2 pi I alpha and e to the minus 2 pi I cancel out, leaving you with just R e to the I theta to the minus alpha, which is Z minus Z naught to the minus alpha, times W of Z, and hence just G of Z. So in other words, G of Z goes to some new function G of Z minus G of Z goes to some new function, let's call it G tilde of Z, which differs in Z changing its phase. But that G tilde of Z is nothing but G of Z, as we've just shown. So G of Z is single valued as I traverse Z naught. Well, that means that a solution of this first order linear differential equation then can be written as W of Z, sorry, what was that? The unique solution of the ODE can be written and we've just shown, we've constructed this right now, can be written as W of Z equal to Z minus Z naught to the alpha times G of Z for G of Z, some single valued analytic function. Okay, any questions about this particular example? All right, this is the simplest case of the of this construction that we can that we'll encounter. Next time, because I see we're over time, next time I'm going to show you how we generalize this method to some nth order linear differential equation. And again, we solved the first order one. It was straightforward enough. We could solve it by inspection and write down an integrating factor, blah, blah, blah. But we're also able to show that without solving this differential equation, we can put the solution of the differential equation, if you will grant me that solutions of such differential equations are unique. Again, one can prove this, I choose not to. But if you will grant that the solution of the first order differential equation is unique, then I can always put it into this form without even solving it. Okay, this form we'd read off previously from thinking about the form of P of Z, but you can see you don't even need to do that. You just need to make some assumptions about P of Z and you can put it into this form. Any questions? Okay, if not, then I will see you on Tuesday. Thanks, everybody.
Thank you so much.
Thank you.